Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. First, let me introduce myself. I am Shofirul Nisa from Chemical Engineering Universitas 11 Maret. Today, I'm going to talk to you about my research. The title is Preliminary Investigation of NiO Anode for NCA and NiO Battery from Spent Catalyst Recovery. My presentation is divided into 4 parts. Firstly, I'm going to explain my research background. Secondly, about materials and methods. Then about my research results and discussion. And finally, conclusion. Let me start by giving you my research background. Spent nickel catalysts are nickel catalysts that are less active and lose their catalytic function due to repeated use and contamination of chemical processes. Spent nickel catalysts can be recovered through the use of nickel metal. The main reason for recovering nickel are environmental safety, because if catalyst recognition limit has been exceeded, it will become solid waste. The method most widely used for recovering nickel from spent catalysts is acid leaching. There were several studies that discussed metal recovery using this method. One of them was Ramuscano recover nickel from nickel aluminium trioxide spent catalyst. This catalyst contains 11.2% nickel and 88% aluminium trioxide, which was treated in 50% nitric acid solution. Nickel can recover about 85% at a particle size of 75 micrometer and operating condition of 65 degrees Celsius for 2 hours with stirring speed of 600 rpm. Recovery spent nickel catalyst can be used as lithium-ion battery anode. There have been many studies on the use of NiO as anode, but NiO derived from spent nickel catalyst doesn't yet exist. Moreover, NiO as anode and nickel cobalt oxide or NCA as cathode have never been done. The electrochemical performance of NCA, which reached 200 mAh per gram, is expected to be a support for NiO NCA batteries. Finally, we have the spent nickel catalyst to be used as battery anode and NCA as cathode. Then, about materials, spent nickel catalyst was obtained from Petrooxo Nusantara. The extruded sheet spent nickel catalyst was treated by crushing and sieving through 100 mesh screen. Citric acid and hydrochloric acid were used as leaching agent to separate nickel from other metals. Oxalic acid and sodium hydroxide was used for precipitation agents. And next, the methods. For acid leaching, 20 grams of spent nickel catalyst powder was leached in 1 liter of 1 molar citric acid and 1 liter of 4 molar hydrochloric acid in different beaker glass. These two acids will be compared. The leaching process takes place at temperature of 70 under 80 degrees Celsius under stirring for 3 hours. Leaching results were separated between filtrate and residue. To obtain nickel oxalate, the filtrate was precipitated with oxalic acid at 60 degrees Celsius under stirring for 2 hours. Precipitation results were allowed to settle, washed to inotropic edge, and dried in an oven. The next step, the powder form was reacted to oxygen and sintered. Furthermore, the sample was called NiO I. Then, for the method direct sintering, the sintering process was done by heating the spent nickel catalyst powder in a molten furnace at 8 degrees Celsius for 12 hours. The results of this direct sintering were NiO2. Characterization was done by finding out the material properties. The structure of the crystal was investigated by XRD. Metal ion concentration was analyzed by AAS. Organic and inorganic materials was identified by FTIR, and elemental composition was investigated by XRF. Electrochemical performance was carried out using cylindrical batteries, cathodes, parators, and electrolytes used NCA sheet, silicate, and lithium hexafluorophosphate, and NiO as anode was mixed with NMP to form slurry, then coated on CU foil. Then the anode sheet was dried in vacuum oven at 80 degrees Celsius overnight until it was ready to assemble. The performance test was analyzed using newer battery analyzer and PDF software. Then about results and discussion for FTIR analysis. First, it is necessary to know the elemental composition in it. FTIR test showed the presence of NiO, MOO, and OH, and then the test was proven by the XRF test showed that the most dominant compound in the spent catalyst was NiO, followed by molybdenum trioxide. The high concentration of NiO can prove that if it not utilized, it will suffer losses, and if it is disposed, it can pollute the environment. Then, for AAS results, the leaching was carried out into variation of acid, citric acid, and hydrochloric acid within the same operating condition, but the concentration of the solution was different. Citric acid was used as leaching agent because of its ability to dissolve nickel, as well as hydrochloric acid. 20 grams of treated sample recover 11 grams nickel and in 1 molar citric acid and 15 grams nickel in 4 molar hydrochloric acid as shown in the figure. Nickel recovery using hydrochloric acid gives a higher yield because the chloride ion has high connectivity to the metal and the condensation used is also higher. And then the XRD analysis. The results of precipitation leaching in the form of nickel oxide were analyzed by XRD. The material in this study can be indexed to a pure cubic phase nickel oxide consistent with GCPDS card. However, there were other peaks that appear so that there is still impurity in the product. After acid leaching and precipitation, the next step was to change nickel oxide to NiO with remaining composition. The XRD and NiO shown in figure that all peaks are compatible with GCPDS card. That means there is no impurity in NiO. The process with acid leaching can react with molybdenum trioxide. Whereas in NiO2, molybdenum trioxide impurities were still detected because the treatment was only sintering. Further treatment is needed to eliminate this impurity by increasing the temperature and the time of sintering process. And the last for electrochemical performance was tested by a cylindrical battery consisting of NiO2 as an anode and NCA as a cathode. This test used galvanostatic charge discharge, and discharge capacity obtained in this study was still low at 37.210 mAh per grams, as shown in figure. The presence of Bayer-side reaction during this process of charge discharge and pure battery fabrication can cause low discharge capacity. And the last for conclusion, first, spent nickel catalyst consists of dominant components 90% nickel oxide and 6% molybdenum trioxide. And second, recovery spent nickel catalyst has been done with acid leaching and sintering process. The use of hydrochloric acid is better than citric acid. Then the XRD patterns of NiO and NiO2 are compatible with GCPDS. Then battery performance testing, the discharge capacity of 37.210 mAh per grams was obtained. Finally, further studies are needed so that the spent nickel catalyst can be utilized properly as an anode of lithium-ion batteries and as a material that can be combined with NCA. For acknowledgement, this paper is supported by Indonesia Endowment Fund for Education or LPDP/Lembaga Pengelola Dana Pendidikan through pendanaan riset inovatif produk or RISPRO Invitasi Grant number PRG6/LPDB/2020. We also acknowledge Petroxo Nusantara for providing the spent catalyst for this project. Thank you.